this the one you were saying?
No, it's iodine. Yeah.
Okay, this is what Nina just asked about. If I took this as my central atom, 1, 2, 3, 4 things around it. If I took this as my central atom, 1, 2, 3, 4 things around it. So that's not this case. Okay, so hang on to that one. We'll come to it. Marco.
Is there a special case around that?
Okay, if you look at that, that's like section, I think it was 8-10, where they had HF. And I said, boy, it's dumb to do, because if I got HF, I know it's linear. There's just 2 atoms in it, and I know it's polar. And I know a whole bunch of stuff about it, and I don't have to go through all this work.
Okay, so we don't have to take one atom as central. Okay.
Yep. Now, let's go onward here with our... We did BF3 using the VSEPR theory. We could have done BF3, BCl3, BI3. All of those would have come out to be the same. And the VSEPR theory for this one told us trigonal planar. What would those bond angles be? 120. Now, that was from the VSEPR theory. Let's think about this new theory. And when you think about the new theory, the VSEPR theory emphasizes the needs of the central atom, not the stuff out around. Like the VSEPR theory does that. The valence bond, if I got that wrong, valence bond is thinking about the central atom. Okay, so we look at electron configuration. So we find boron up there. Okay, we know boron has what core? Helium core. Take it from there, Bruce.
2s2, E1.
Okay. Now, this is a box diagram, but it's a partial box diagram, just showing valence electrons, because that's where the action is. Okay, if I were to look at this, and Bruce is absolutely right. If you've got beryllium just sitting around minding its own business, not bonding or wanting to bond with anybody, that's great. But if I were to look at that, I would think boron would only bond with one fluorine or chlorine or whatever, because it only has one unpaired. Because remember how I bonded with Andrew? Unpaired to his unpaired, and we overlapped. Okay, so here's where we go into fantasy life again. Let's promote. (2s), 2p. Now it would be stupid to promote into this orbital because you haven't gained anything. So when we promote, we're going to go into an empty p. Now, I could visualize, here comes, first fluorine comes in and overlaps here, second and third. Okay, same story you heard before. This story is very repetitious. Okay, if this were reality, we would expect the bond with this 2s to be slightly shorter and stronger than these other two, and that's not what's found in a sophisticated lab. We find this, this, and this are identical in length, meaning from nucleus to nucleus, and strength, how much it takes to break it. So there's something wrong with our theory, so this is where we go to our next stage in our fantasy life. And we say, hey, let's take those three and let's somehow mix them or hybridize them. And if you take 3 atomic orbitals to mix, you will end up with 3 new hybrid. They are named sp2. And then that 2p, we didn't need it. Now, they will also talk about each one of these has 1/3 S character and 2/3 P character. They don't mean shape, they mean in energy. And if you look in your book, what they try to do is when they draw those hybrids, it's like 2/3 of the way up here. And then this P would be slightly higher. but that really doesn't concern you now, but that's what they're talking about. The name tells you what mixed. So an S and two P's mixed, and they use that as a superscript. Okay, story is, you have that boron in the middle. It's got 3 new hybrid orbitals. They want to spread out to get as much turf for themselves as possible. We already know what the best shape is. Trigonal planar. So if you look up there, you've got your central atom, okay, an sp2, an sp2, an sp2. Each one of them has an unpaired electron. Here comes a fluorine, here comes a fluorine, here comes a fluorine into bond. What's the bottom line? You have 3 things. sp2. Now look in your lab 15. Spot me something with 3 things other than just that one we did. Oh, 3? Good. If you do ozone, O3, you have, here's your central atom, one of the oxygens. You have 1, 2, 3 things around the central atom. Okay, so you point at that, you say hybridization state on that is sp2. Is there any others that you see there? Any others with 3 things? Excellent. AlC3, because aluminum violates, it just needs 6. So it's got 3 things around it. So hybridization state on that is going to be sp2. Okay, now, next case. We did CCl4. And this is what we came up with. This is from the Vesper. We came up that it was tetrahedron. Same old story that you've heard twice before. If you took that to a sophisticated lab, everything we predicted about it is nonpolar, the bond angles are 109.5, it's a tetrahedron, it's fantastic. Well, let's take this second approach, the valence bond approach, and let's think in terms of the needs of the carbon. So we want to look at its electron configuration. So we spot carbon up there. We know we got a helium core. Alex, where do I go from there?
Three.
Okay, you got a helium core, and we got to go from there.
So
2s2. Does it have more? Perfect. And I'm drawing them like that by whose rule? Hutton's rule. Okay, same old story. If I look at that, or you look at that, how many chlorines do you think this would bond to? 2. 1 here and 1 there. This is what we find. Okay, so in our bag of tricks, we're going to promote one. So we have the 2s, the 2p. That doesn't cost you much in energy. Now I can understand how 1, 2, 3, 4 chlorines can come in and overlap and it looks fine. Okay, but we find, same old story you've heard twice before. If something overlapped with the 2s, this should have a stronger, shorter bond than the ones that overlap with 2p, and that's not what's found. Every bond here is identical in length and in strength. And so, in our bag of tricks, we think, what if these somehow mix together or hybridize, to use the fancy word? If you mix 4, you get 4. Take a wild guess what they named them.
sp3.
Just sp3. You don't say which S or which P, of which level, is just standard. sp3 got mixed. And that's the name of each of these orbitals. So we come over here, bottom line, if you have four things, sp3. sp3. Now, look up here, and I won't try to draw this one. You've got something in the middle. You've got four lobes now, these new hybrid orbitals from the BB approach. Tetrahedral, and that's what it's going to look like. So a chlorine can come in up here, over here, and over there. Can you find another one that has four things around it on your lab 15?
That's you, all one used it.
CH.
SEH2.
SEH2. Great. Great. Because selenium is going to have two lone pairs. Okay, so selenium, four things. So here would be your question. What's the hybridization state on your central atom? You count things, it's always sp3. Here's a great memory device. Okay. Because this is really all you need to get out of this is what the hybridization state at this point. Now, organic chemists go into this a lot more. Remember how chemists are lazy and they don't write the ones who are understood? If you would add up the superscripts, they will equal your number of things. So 1 and 1 is 2, 1 and 2 is 3, 1 and 3 is 4. Okay, are we okay so far? Anybody spot any more that had four things around it on the lab 15?
ICL3.
Wait,
NH2 minus 1.
NH2 minus 1. Did they have two lone pairs on it?
Yes.
Is it going to come out like that?
Yes.
Okay. Yeah. If it came out like this, then sp3 is your hybridization state for that nitrogen. All right, let's go on. I think you see the trend. PF5. Okay, we did it. Vesper theory predicted that. Trigonobipyramid, and oh yeah, you know the story. That prediction is absolutely correct. But let's think for this second theory, valence bond. So we think in terms, what are the needs of the phosphorus? So we have to look at electron configuration. If we're doing electron configuration of phosphorus, who's the core? Neon. Okay, let's build from there. Meredith, can you build from there for me, neon core, and then you tell me why? Phosphorus. Just count over.
Oh, 3. Sorry.
Okay, same old story. If you do look just at this, how many fluorides do you think would bond to phosphorus? 3. Boom, boom, boom. Okay, and yeah, that does exist. That's a compound we may have seen or worked with before. However, if you use really harsh conditions, you can force that phosphorus to accept not just 3, but 5. So, in order to bond with 5, we've got to promote. We have 3S, 3P, 3D. And if we're going to promote, it would be really dumb to take this and promote just to here. That doesn't help us a bit. The D's are working out there, even though they're unoccupied. We promote into the D. And you know the story, that if it overlapped with this, it'd be a shorter, stronger bond. If that's not found, all those bonds are identical in length and in strength, which is the only way we have to measure them. And so we think hybridization And you take 5 here and mix them. We leave those 3 Ds alone, these out here. Take a wild guess what you name it. SP3D. Yesterday in my class, somebody goes SP4. Well, any energy level, there are not 4 p orbitals. So you got to move, after the 3 p's are filled, you move into a d. So this becomes SP3D. Okay, now we're out of time, but if we went through, and the next case that I was going to do, let's see this, SF6 that we did, octahedron, all of that would be true. You'd hear that same baloney you just heard. Promote, but this time you have to promote twice. That's okay, a little bit more energy. Then you hybridize. And so what would this last one be? Perfect. Okay, now you're in a position to go back in that last column. You may have done that before because I think I put a cheat sheet up there, but this is where it's coming to.